Kate BYP with the second video about heat sinking, and I want to show you a real example, especially since this kind of radio is very popular this era. Lots of them out there still being used, and I have done a video on recapping this radio. In particular, this IF board on top with a 3-terminal regulator. I think that's a 3TR also. And over here is a 5-pin audio IC, and I forget what that tab package is. Those are called tab packages, TO220. See the white plastic insulator insulating the screw from the metal chassis. And this heat sink isn't really intentionally grounded. It doesn't need to be grounded, but it is grounded. Notice basically no heat sink grease spooging out. Notice an insulating washer. No sloppy grease, no sloppy grease. No sloppy grease. See the Loctite. This is the difference in having 40 some odd years experience in doing this for real versus just playing hobby. And I'm going to illustrate in this video why amateur radio is not a hobby and the disaster that can occur if we treat it as a hobby. I thought about doing this next video on the particulars of this, joining these devices, these transistor IC devices to a heat sink, but this information is so important and so widely applies that I'm not going to do a video on that. What I'm going to do is actually put an article together for CQ magazine, because this needs to be more widely published than likely that my channel is going to get. And that goes into what happens when we fail to treat this heat sink grease as a thermal insulator, which is what it really is. This goes someplace very bad. But the reason for focusing on this radio is coming across a video on YouTube on this radio, and the horrifyingly bad advice that completely contradicts the laws of physics that I put in the first video, violates every point of thermodynamics and heat transfer, and does a very poor job by a very well-meaning individual. It's a nice video, but it's completely wrong. Restoration of this radio absolutely must include taking that final block out and reconditioning the heat sink and cleaning and re-greasing the devices. And that wasn't done, and this radio is not restored and not fit to use, especially in sideband processor, without doing that. There's two things extremely bad to do with this radio. The first one is to fail to recondition that final assembly unit. And what must be done there is actually scrape down, plane down the heatsink block, because after time, these contacts, especially with the screw between the tab of the transistor and the heatsink, will actually cause a depression in that aluminum. The aluminum is very soft. Now, these tabs are some form of copper, brass, something or the other, plated with tin or nickel. But that contact and that heating and cooling will actually distort that heatsink surface, even a thick one back here on the finals, and deform it so it loses mechanical contact and heat transfer contact between the tab of the device and the heatsink. And it is not acceptable to put heat transfer compound between these two metal pieces with voids and gaps and think that that's going to be sufficient, because, as I mentioned in the first video, heatsink compound is not a heat conductor, it's a heat insulator. The data I've looked up online about heatsink compounds says that their thermal conductivity in watt meter Kelvin is on the order of point something up to 4. That is a miserable heat transfer. Air might be 0.03. So a heat sink compound is marginally, it's kind of times 10 better than nothing. So, but I'm gonna leave those details for the CQ article. What I want to focus on in this radio is two ways to totally blank it up, and refusing or failing to recondition that unit's the first one. It won't show up until you operate it in sideband with a speech processor on, which raises the duty cycle, and that's the only time in this radio that fan comes on, and it gets good and hot back there. And by the way, I ran one of these on field day in 2015, 106 degrees ambient. You talk about hot. The other way to activate the built-in hand grenade in this unit. Notice a DC 13.8 volts. Do not exceed that. I did exactly correct work on this radio. I know it. I've replaced a pile of devices like this with heat sinking and grease to cover this bench top in my lifetime. I've done a lot of it. Using it on that MFJ power supply with the Yaesu 857, with that voltage turned up to make the Yaesu happy of just a shade under 15 volts, and I didn't know why this radio would overheat and shut off. This top cabinet above here would get so hot I couldn't touch it. And then the audio would go out. I'd turn AF gain up, nothing. Shut off, cool off, work again. What's happening is apparently that 3-terminal regulator does not like that high input voltage and gets extremely hot. Now put excessive grease between that tab and that heatsink, and that's a recipe for destroying that 3-terminal regulator. It should or may have internal limiting, but if and when that fails, and that regulator is a series pass regulator, and if that pass transistor overheats and breaks down, collector to emitter, that's going to dump 13 volts on this 5-volt microcontroller and blow it to hell and back. And that will be the end of this radio. That controller is down inside there. I think it's a 40-pin dip, a typical 1980s processor. But those 5-volt ICs, especially that processor, will take that overvoltage for, I don't know, 10 milliseconds. Flash Gordon is not fast enough to hit that power button before that IC is destroyed. And that's the end of this radio. So there's the path forward and failure analysis to how to do incorrect or don't do heatsink work and totally destroy this radio and make it worth nothing but parts or one of a pair of bookends. I'm going to show you a couple-minute segment out of this video I've been referring to, but I want you to see these parts up close. The nice individual who made the video improperly handled these boards, took them out, handled them with bare hands, no static control, no grounded static mat. The human body model for ESD, electrostatic discharge, is up to 3,000 volts. Shuffle across the floor, sit down, and touch that crystal in the wrong way, and that's the end of the crystal. Any of these solid-state devices can or will be immediately destroyed by a static discharge of a fraction of that. Even these TO92 transistors, many of them are only good for 50 volts. And the trouble with transistors, and especially MOS, these early MOS ICs, which may not have been protected by TVS or Zener devices on the pins, is that destruction is absolutely immediate. The discharge does not need to draw any current. Just the presence, just the contact of excess voltage is enough to finish them off. It pulls the junctions apart. This video is on a channel, Kenwood TS 430 Restoration Series, and it's a recapping video. It's not doing restoration. It's left way too much stuff out. And this information, these procedures are not just bad, they're what I call cringe-worthy. It just makes my butt pucker to watch this, to know the damage is being done without having a clue. But starting at about 45 minutes, and if this doesn't appear too clear in my video, and if the audio doesn't necessarily come through, look at this Kenwood TS 430S Restoration Series Part 3 for a very good example of doing everything absolutely wrong with a very great chance of causing damage. So I'm going to pull my mic and try to pick up the audio from the computer speaker, and I'll explain here and there why this is extremely bad advice. So here are the four tabbed devices. 1, 2, 3, 4 have been put on the heatsink with excessive heatsink compound, which is a thermal insulator which separates the tabs from the heatsink so they can't make metal-to-metal contact. thus destroying the best heat transfer that there is. The first gross mistake.
Get the right screwdriver here. Gotta go inside the hole.
Good and firm is an opinion. When those screws are over tightened, as these are, yes, fingertips, but the diameter on the handle is several times bigger than it should be, and that magnifies the torque. And that will cause pull through the threads. That will cause serious deformation of the tab on a device and the heat sink. It happens over time. You won't know it till afterwards. What that does is that breaks contact between the rest of the metal tab on the back of the device and the heat sink, and leaves only grease between them because too much grease was applied. And that leads to overheating that gets worse as those screw threads give way over time and break contact and the screw comes loose. When I did it, I made sure the threads were clean. I put blue Loctite on them and I just touched them down and let them rest for hours so that the Loctite set up and they will never come loose. Now if you'll notice, no anti-static protection, no static strap. Picking up this board with static sensitive devices with no protection. Very bad. The other problem with too large a screwdriver, it allows cross-threading the screw, and that destroys the threads in the aluminum. And those are steel screws threading into aluminum. And the aluminum is extremely soft, especially because the threads are a ramp. They're a wedge. And that what appears to be a little bit of torque on that screw translates into a tremendous amount of pressure on those threads.
Chassis, the ground.
Screw it down. How much?
Make sure that centers, otherwise you won't be able to screw the screw in all the way.
Yes, center it, but how much torque?
We just want to get these good and firm.
Good and firm. There is no such thing. That's an opinion. In a manufacturing facility, I would take him off the line. In a manufacturing facility, we use torque limiting screwdrivers because remember, ounces, inch of torque, extremely small, because anything close to a pound-foot's too much. And yes, I've done manufacturing engineering and electronics. Coming up, and don't worry if there's thermal paste in the hole and on the threads. Okay, listen closely.
Don't worry about if it's got thermal paste in the hole. It's just going to make the screw conduct heat too.
Okay, that's rolling on the floor laughing. The grease is a thermal insulator. Put it in the threads. The threads are lubricated. The threads will come loose. The screw will come loose. The thermal contact between the device and the heatsink will break, and the tab device will be destroyed. When there's grease in the threads are not making metal-metal contact, and as we saw in the first video with the heat transfer properties of the materials, metals have an extremely high transfer, and that grease has extremely low. Steel, 50 watt meter Kelvin, aluminum, 230. The grease, 0.5. So putting an insulator in the threads does not help the screw conduct heat. This grossly violates the laws of physics. This is what's known as a compensation mechanism with a dismissive attitude, a dismissive statement. Don't worry about doing a sloppy job. I'll just excuse it by making up this thing which grossly violates the laws of physics. And this right here is an example of why amateur radio is not a hobby. Because this hobby mistake may spell the end of that radio by the failure mechanism I just explained to you. And coming up, another dismissive statement and attitude to excuse doing a sloppy job putting too much heatsink compound between the device and the tab.
Now, let's see if y'all can see this.
See the sloppy job?
Squished out
yes, and it shouldn't
along
be.
the edges. Let's get the glare out of it.
That is sloppy.
See how it's squished out along the edges of the tab?
Okay, listen carefully.
There's nothing wrong with that. I mean, don't put...
There's nothing wrong with it because why? Notice No idea why it's good or bad. No defense of that statement, no source. Let me tell you, it's extremely bad. It's put excessive heatsink compound, which is a thermal insulator between the metal tab and the metal heatsink, which are supposed to be in contact to transfer heat. Instead of having metal-to-metal contact and the grease to fill a couple of small depressions or asperities to make up for not having air in between, he has put way too much compound in, and tightening the screw down will not squeeze it out. There will still be a thick layer, 5, 10, 15, 20 thousandths thick, that all that heat must screw through that insulating heat sink compound. And that causes a thermal barrier between that device and that heat sink. Extremely bad. That single steel screw with extremely fine threads into very soft aluminum cannot apply enough torque evenly, or cannot apply enough torque to create enough clamping force evenly without distorting that tab on that transistor, or on that regulator IC, without distorting the tab and causing a gap down at the bottom where the back of that IC body needs to contact the heat sink. This is extremely bad work, and is a real risk of destroying that regulator and possibly wrecking the rest of that microprocessor system. But having no clue what he's doing, God bless him, he just makes this stuff up and dismisses doing bad work by making up this "it doesn't matter." I'm here to tell you from the laws of physics that it does. The mighty RCA Corporation, about 1981, made the mistake of doing this, and they paid for it dearly. In the CTC chassis portables, color TVs, about 1981, they had assembly workers just like this fellow who thought that they could put a bucket full of heatsink grease on each horizontal output transistor on the back of the chassis at the bottom and slap them on, and they thought that tightening the screws would squeeze the grease out, and it did not. Because the grease is not very compressible, it doesn't flow well, and there can't be enough torque applied to those screws to create enough clamping force to do that. RCA paid through the nose and out the you-know-what because those TVs blew up one after the other because they put excess heatsink grease on the horizontal output transistor. They overheated, shorted, and the sets came in by the tens and the dozens. Complaint, no picture, no sound, dead. The first thing we did, took the back off, ohm meter, chassis ground on the tab on the case of the TO3 transistor, dead short, and that transistor and the mica insulator and the chassis just covered with light blue grease. Scrape the excess off, clean the surfaces off, take a little tiny dab of that grease, smear it in the surfaces, clean the excess off the washer, put it back together, worked perfectly. But this is just a horrifyingly bad work here. Okay, more rationalizing.
Along the edges of the tab. There's nothing wrong with that. I mean, don't put so much on there that you just make a mess. But
well, you did.
It's not going to hurt to have a little extra on there. It's going to make sure it fills all the little gaps in.
Oh, it's going to fill all little gaps in that shouldn't be there in the first place. You're going to fill a gap in with an insulating compound. Yeah, if there are gaps there. But see, originally there weren't. Now in this old unit that's had years of heating and cooling and thermal expansion and distorted that heatsink surface and distorted the tab on that device, there are going to be bigger gaps and voids. And you're going to fill them with heatsink compound and fill the gaps. But also putting that much heatsink grease on the back of that device will prevent any metal-to-metal contact. It will only be through the screw contacting the tab and squashing it into the heatsink and deforming the area around it. And this is a recipe for disaster.
Along the edges of the tab. There's nothing wrong with that. I mean, don't put so much on there that you just make a mess. But
how much is that? Quantify
it's not going to hurt to have a little extra on there. It's going to make sure it fills all the little gaps in. It'll squish out what it doesn't need.
It will not squish out what it doesn't need. There isn't enough clamping force to take that very thick, viscous grease and force it out. It will bend the tab. Try it. Try it for yourself. Put a thick coating of grease on there, tighten that screw down, then take it back off. Did it squeeze out the excess and leave metal-metal contact? No. If the goal is to fill the voids but not have extra that needs to be squished out, do it right in the first place, rub the grease in, and scrape off the excess, then assemble it. Then there's a chance for metal-to-metal contact, which has good thermal contact, but this is simply horrifyingly bad. Now let's grossly over-tighten this screw. Now this large diameter handle, using 4 fingers, a strong man. Now watch this. At that point, that's plenty of torque. Now this is ratcheting those threads down, so it puts that copper brass tab in contact with that soft aluminum, and that has extruded. That's already extruded this heatsink tab, the metal around the hole. It's already extruded that back into the aluminum and created a bump. And that's the only place around that screw, because this is over tightened with too much grease, that's the only place there'll be metal-to-metal contact and good heat transfer. And again, try it and take it apart and look at it. And that's what I did back in the day when I was learning this. I would actually experiment with these things. But see, I didn't just replace 1 or 2. I replaced dozens and hundreds. And now a gross contradiction. Previously, not using too much that made a mess, we just used enough. And trying to compensate for that by the myth that the screw will squeeze the excess out, and then this contradiction.
The extra out of there.
Cleaning the mess off that he made by using too much grease, which, by the way, is a waste of time. This doesn't accomplish anything. Had too much squish out on most of these anyhow, contradicting a previous statement and admitting there is excessive compound in between, and it will, not maybe, will result in these devices overheating and possibly failing. And remember what I told you about this one? This one leads to a catastrophic failure that destroys that microcontroller, and that's the end of the radio. In fact, one would be real wise to just replace that one. I think it's a 7805. Okay, I can't stand to watch any more than that. In a manufacturing setting, this guy would be off the line immediately. And out for some training, because I would not let something this horribly done pass through manufacturing. Again, the mighty giant RCA Corporation did, and it came back to haunt them. So, I haven't made the second video to tell you how this should be done. There's most of the information needed here in the first video on the thermo and heat transfer principles, but you can probably figure most of it out. But I wanted to show you this stunningly bad example of how to do this and do everything exactly wrong. And sometimes it isn't enough to look at how to do it correctly. We need to understand how mistakes happen, because some of this stuff's pretty subtle, like the deformation of the screw threads. And in factories that do assembly and manufacturing, all these details are dealt with by engineers. And I have been there and done that as an engineer in manufacturing. And again, this is an example of not being able to do this any worse, except maybe take a hammer out and try to pound those screws in. So again, a cringeworthy video that you really should watch that segment. It's from about 47 minutes up to about 50, but I simply can't watch any more of it. KBYP out.